Alright, so in this video, we get into some real chemistry, okay? So chemistry is by definition the science that's concerned with how matter is organized and how one type of matter is converted into another. And for the longest time, there were two views about matter. The first was the idea that matter is composed of atoms. That if you took a sample of an element and you divided it into smaller and smaller and smaller and smaller pieces, sooner or later you would get to a point where you could no longer subdivide. Okay? And that point you would have an atom. And this idea goes all the way back to the ancient Greeks. And the opposing viewpoint was that matter was continuous, that it was infinitely divisible, that there would be no limit to how small you could go dividing your sample into smaller and smaller pieces. And this was supported by some of the predominant thinkers at the time. But all this was, at the time, was simply an idea, because there was no science as we understand it today to prove or disprove these ideas. Alright, so it was a man named John Dalton in 1808 who made this proposal and rekindled the atomic theory of matter. So he said, first of all, that all matter consists of tiny, indivisible particles called atoms. Okay? Atoms of one element cannot be converted into another element. You can't change lead into gold, as nice as that might be. So chemical reactions rearrange the matter that's already present, but they don't change one type of atom into another. Okay? So atoms of one element are different in mass and properties from those of another element. So let's say that a carbon atom is somehow different than a silicon atom, or an oxygen atom is somehow different from a sulfur atom. And last is compounds result from the chemical combination of a specific ratio of atoms from different elements. So what's the modern view of an atomic structure? I'm going to skip most of the historical stuff. What do we know today? Where does this become important to us today? That the atoms are composed of three smaller subatomic particles: proton, neutron, and electron. Okay? So the proton carries a positive charge and has a mass of 1.0073 atomic mass units. The neutron, as its name implies, carries no charge and has a mass of 1.0087 atomic mass units. The electron carries no charge and has a mass of 5.486 times 10 to the minus 4. Now, note that these two are roughly the same. A neutron is ever so slightly more massive than a proton, but this is orders of magnitude less massive. In fact, it would take about 1,800 electrons to equal the mass of a proton or neutron. Right? So the protons and neutrons form the nucleus of the atom. Okay, that's where most of the mass is located. And so the nucleus is relatively small, or small relative to the size of the atom. A common analogy is that if an atom were the size of a football stadium, the nucleus would be the size of a golf ball. Right? So atoms are mostly space. And most of the mass of an atom is concentrated into that very small space. Now, also important that in an electrically neutral atom, in other words, one that does not carry a charge, the number of protons equals the number of electrons, right? Because the protons carry the positive charge and the electrons carry the negative charge. So if your atom is neutral, then the number of positive charges has to equal the number of negative charges. Okay, so there's two things that we need to talk about: atomic number and mass number. Okay, so the atomic number represented with Z, okay, this is the number of protons in the nucleus. Okay, atomic number tells you the number of protons, right? So one of Dalton's hypotheses that atoms from one type of element are different from another type of element. Well, of course they're different. They have differing numbers of the subatomic particles. Okay, now the atomic number also tells you the chemical identity of the element. Okay, and these are the whole numbers that you see associated with the elements on the periodic table. We'll talk about that in a minute. Now, mass number, A, is the total number of protons and neutrons in the nucleus. Okay, because neutrons don't carry a charge. An atom can have a variable number of neutrons, and so mass number can vary even between atoms of the same element. Now, mass number is usually represented with a superscript before the chemical symbol. So, for example, if you see something like this, we'll use boron as an example. If you see boron 11, that 11 is the mass number, the number of protons and neutrons. That's the mass number. All right. So this is where we get into isotopes. All right. So isotopes, like we said, neutrons don't carry a charge. So an atom can have, even atoms of the same element can have differing number of neutrons. This is the definition of isotopes. They have the same number of protons, but a differing number of neutrons. Okay, so for example, if we looked at two common isotopes of boron, boron 10 and boron 11. Now, boron has 5 protons. We could figure that out. You could get that from the periodic table. We're going to talk about that. Okay, so if you have 5 protons, and your total number of protons and neutrons must add to 10, right? Because the 10 is the mass number, then you have 5 neutrons. But if you have a mass number of 11, then your total number of protons and neutrons now adds to 11, so you have to have 6 neutrons. Remember, the protons tells you the chemical identity. It doesn't have 5 protons, it's not boron. So we know if it's boron, we know the protons are 5 protons, right? So if the mass number is 10, then you have 5 neutrons. If the mass number is 11, then you have 6 neutrons. Okay. Same thing with carbon, which is right next door to boron in the periodic table. Now, carbon has an atomic number of 6. So it doesn't have 6, so we know it's going to have whatever isotope you're dealing with. If it's carbon, it's got 6 protons. So carbon has 6 protons. Carbon 12 has 6 protons and 6 neutrons, right? Because 6 and 6 add to 12. Whereas carbon 13 has 6 protons, but now 7 neutrons, right? So because 6 and 7 add to 13. So carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, right? So this is the definition of isotopes. They have the same number of protons, but differing number of neutrons. We could also say that a different way and say that they have the same they have the same atomic number, but a different mass number. Right? So let's talk about atomic weight then. Now, atomic weight is the decimal number that appears with an element on the periodic table. You see, why would we not report mass numbers on the periodic table? Because most elements occur as multiple isotopes. So which isotope would you report? So the atomic weight is the weighted average of all the naturally occurring isotopes of the element. So for example, boron, which I've previously used as an example in the last slide, there's two common isotopes, boron 10, boron 11. Okay, so boron 10 has a mass of 10.013 atomic mass units, and that's 19.9% of your boron. Okay, and boron 11 has a mass of 11.009 AMU, and that accounts for 80.1% of your natural abundance. So what's your atomic weight? Okay, so you take 19.9% of 10.013 and 80.1% of 11.009, and you add that up and you get 10.8. Three significant figures, you get 10.8. That is the atomic weight of boron. But note that 10.8 is a whole lot closer to 11.009 than it is to 10.013, right? Because these two aren't equal. There's much more. 80% of your, on average, 80% of your boron is boron 11, right? So your atomic weight is going to come out to be closer to this number than to this number. Okay? If you like, you could think of the 10.8, you could think about that as being the average mass of a boron atom. So this leads us to the periodic table. Periodic table is a listing of the known elements. Okay? Now, of a listing of the known elements. So there's basically three pieces of information listed with each element. Okay? The chemical symbol, the atomic number, and the atomic weight. Okay? So the decimal number, right, that's the atomic number. That tells you the number of protons. So if we're going to keep picking on boron here, if you were to find boron on the periodic table and has an atomic number of 5, that's how you know it has 5 protons in the nucleus. Atomic number, number of protons, the chemical symbol. Some of these chemical symbols are pretty obvious, like B for boron and C for carbon. Some others not so much. And then there's the atomic weight. That's the decimal number, right? So to all the way out to 5 significant figures, boron's atomic weight is 10.811. Okay? So basically, here's your very first look at a periodic table, right? You have basically had 18 columns and a number of rows. So the periodic table is arranged so that elements with similar chemical properties fall into groups. The columns on the periodic table are called groups, and the rows on the periodic table are called periods. Okay? So group 1, okay, so the columns are called groups, so that very first column, that's called the alkali metals. All right? So that would be this very first column right here. That's the alkali metals. That's hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Okay? That first column, that's the alkali metals. The next group over, that is the alkaline earth metals. Okay? So beryllium, magnesium, calcium, strontium, barium, and radium. That's the alkaline earth metals. If we fast forward over to the right side of the periodic table, the next to the last column, that's the halogens. Okay, that's group 17. Fluorine, chlorine, bromine, iodine, astatine. And then this very last column, group 18 here, that's the noble gases. Helium, neon, argon, krypton, xenon, radon, right? So group 1, alkali metals. Group 2, alkaline earth metals, halogens, okay, noble gases. Now, the groups 1 through 2 and 13 through 18 form the main group elements. All right, so that's basically the first 2 groups and the last 6 groups. That's in these elements in these 2 blocks. Okay, whereas the ones in the middle and groups 3 through 12 are called the transition elements. Okay, sometimes the transition metals. Right, so here's your transition metals through here. And some of these are familiar from everyday life, and they're of tremendous economic importance. For example, chromium, everybody's familiar with chrome plating. Iron is very commonly used. Copper, Cu is copper. Everybody's familiar with copper. Pennies are made out of copper, or at least copper plated. Okay. So we can divide elements into 2 groups, typically, actually 3 groups. Metals, nonmetals, and metalloids. Okay. So metals are located on the left side of the periodic table. And by left side, really, that left side extends all the way over to about here, at least. So basically, all these elements are metals. Okay, so there's far more metals than nonmetals. So what are some properties that you associate with metals? Okay, they're malleable. What does that mean? That they can be hammered into a sheet. You can take a metal and bend it without it breaking in half. Okay, ductile, meaning it can be drawn into a wire, such as the tungsten filament and incandescent light bulbs. Metals are shiny. They exhibit a characteristic luster, and they're electrical conductors. In fact, they're not only conductors of electricity, they also conduct heat. So they conduct heat and electricity. And most tend to have high melting points. Okay? So the nonmetals are located on the right side of the periodic table. So now we're talking about basically these elements here. Okay, from these right through here. Those are your nonmetals. Okay. Now the properties of these are more varied. They typically tend to have lower melting points. Many are gases. All right. And then your metalloids form a staircase line between the metals and the nonmetals. So they have properties between those of the metals and nonmetals. So for example, that would be these elements right in here. Okay, boron, silicon, germanium, arsenic, antimony. Okay, these are all metalloids. So they have properties in between those of the metals and the nonmetals. So for example, if you look at silicon, it has silvery in appearance, and it kind of has a luster like a metal would, but silicon does not conduct electricity like a metal. It's a semiconductor. So the properties are in between. And we'll stop here and call this the first part of the video.